It is no secret that physics uses math. However, the only tools that are really necessary for understanding basic Newtonian physics are the derivative and integral. So, before we talk about any more physics, we have to do a quick calculus crash course covering these topics. We know from algebra that the slope of a line is given by the rise over the run, or the change in y divided by the change in x. For a linear function, this does not depend on which 2 points you look at, so it is a constant. But what if we have a function whose slope between 2 points is not constant, for example, a parabola? One thing we can do is to find the average rate of change of the function. This is essentially the same as what we did before. If we have a function f of x and we want to find the slope between 2 points separated on the x-axis by a distance h, we can apply the rise over run formula. The change in f is given by f of x plus h minus f of x, where the change in x is given by x plus h minus x, which simplifies to just h. So the formula for average rate of change is delta f over delta x is equal to f of x plus h minus f of x, all over h. Now, what if we want to find the slope at just a single point? We can try to just plug in h equals 0 in the average rate of change equation, but this gives us 0 divided by 0, which isn't very well defined. What we can do instead is look at the average rate of change, but make h get smaller and smaller and see how our average rate of change equation behaves. This process is known as taking the limit. So now we can write our rate of change as df dx is equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. This is known as an instantaneous rate of change, or a derivative. As a simple example, let's consider a general parabola given by f of x is equal to ax squared plus bx plus c. Now we can plug this into our formula for the average rate of change. Note that for f of x plus h, we plugged in x plus h everywhere we had an x in the original equation. Now we can expand this out and we see that a lot of terms cancel. Most importantly, in the numerator, we can take an h out of every term. This h in the numerator will cancel with the h in the denominator, leaving us with 2ax plus ah plus b. Finally, we can take the limit as h goes to 0, and we find that the derivative of the parabola is df dx is equal to 2ax plus b. This tells us that if we drew a line that just touched our parabola at a single point, known as a tangent line, the slope of this line changes as a function of x. There are a few things to note about this result. First of all, the constant c disappeared. This tells us that the derivative of a constant is 0. Furthermore, we can see that our powers in x decreased by 1. bx to the first became bx to the 0, and ax squared became 2ax to the first. This is no coincidence and is in fact true for any polynomial. If we have an nth order polynomial given by f of x is equal to ax to the n, the derivative will be given by df dx is equal to nax to the n minus 1. Another important derivative rule is known as the chain rule, and describes the derivatives of functions that can be written as functions of functions. If we have something that looks like f of g of x, the derivative will be given by df dx is equal to df dg times dg dx. As an example, consider the function f of x is equal to x cubed plus x quantity squared. We can call g of x cubed plus x so that f of g is equal to g squared. df dg will be given by 2g, and dg dx will be given by 3x squared plus 1. Therefore, the total derivative of f with respect to x will be given by the product of these two terms. Finally, there's the product rule for derivatives. If I can write my function as the product of two functions, h of x is equal to f of x times g of x, then the derivative of h will be given by the derivative of the first times the second plus the derivative of the second times the first. So if h of x is equal to x squared times the quantity x plus 1, then the derivative of h will be 2x times x plus 1 plus 1 times x squared. There are many more of these types of rules for derivatives, so much that there is no way that I can cover them all in this video. Luckily, there are many tables of derivative rules and derivatives of complicated functions easily available on the internet. I will leave a link to one or two in the description for those that are curious.